Okay, so welcome everybody to today's colloquium. Before introducing our speaker today, let me just make a brief announcement. The next colloquium will be on December 15th by Morgan Mitchell from ICFO, who will this colloquium is motivated by this year's Nobel Prize, so he will tell us a modern view of entanglement and Bell inequalities. And today we are happy to have our own Licia Verde to give our colloquium. Licia, little introduction in this audience, but nevertheless for the newcomers, maybe just say a few things. So Licia graduated from Padova. She obtained her PhD in Edinburgh, and she held different research positions in, I think, in Princeton and Rutgers before coming here. She joined us in 2007, and she's a cosmologist which has done a lot of important work and well-known work basically on the large-scale structure of the universe. And she has received many prizes, including 2 ERCs. She was also part of the Breakthrough Prize through WMAP. And very recently, last year, she was awarded the Jaume I award for Investigación Básica. And that was the perfect excuse to ask her to give, again, a talk to us. So since you better listen to her than to me, I'll give the floor to Licia. And she will talk about cosmic speedometers.
Thank you. So thank you. It's a pleasure to be here, even though I'm here almost every day, but it's still a pleasure to talk to you about something that I've been thinking about for a while and I've been working on with my group. So, and maybe in some of people's mind. So cosmic speedometer and how to read them. So basically the question is, how fast is the universe expanding? And some of you will know by now that there are two camps about this quantity. And before we start, H stands for the Hubble constant. The little zero means it's evaluated today. Sometimes the little zero drops, but we know what we are talking about anyway. And so this was from the Symmetry magazine, which means that this Hubble issue has made it quite to a wide audience, well beyond the aficionados. And it even made it, I don't know if you follow it, in the XKDC cartoon. And this is for some of the people that are in my group. It goes, there are three main estimates of the universe expansion rate, and they all disagree. Measurement of star distance suggests this universe is expanding at 73 kilometers per second per megaparsec. Measurement of the cosmic microwave background suggests it's expanding at 68. And then Dave was a radar gun and says that it's expanding at 85 miles an hour. So in other words, not all measurements are created equal, and we should keep this in the back of our mind as we go on. So we know that the universe is expanding since 1929, thanks to the work of Hubble and Humason in the Mount Wilson telescope, and we all know the story about the great debate and Einstein and all that. And as a result of this, we have the Hubble law that relates recession velocity to distances with a constant in front, the zero because it's evaluated today, and the H because it stands for Hubble. As an historical note, Hubble relied on the work of Henrietta Swan-Leavitt, who, and in this paper it's a very important relation from 1912, which is a relation between the period and the luminosity of specific stars that pulsates, and these stars were in the LMC and the SMC, so that set out the way to actually calibrate distances, because in astronomy it's easy to measure redshift, but it's very difficult to measure distances. So the luminosities are the proxy for the distances. And it's interesting to know that since she was a woman, that was the time with the birth of quantum mechanics that enabled us to actually interpret physically the spectra of stars. The paper is signed by Edward Pickering, who was the director of the observatory, but at least in the first sentence say that the paper was prepared by Miss Leavitt, because she was not allowed to actually publish a paper back then. So this is important, even in the Hubble plate, you see the Hubble wrote, this is a variable, and then it means follow it up and use this kind of relation to measure distances and get to this scale of the universe. So as a result of this work, then since 1929, we have a relation like this. Now, you can see there is at least one wrong thing in this plot, actually two. The first wrong thing in this plot is that there are no error bars on the data point, and that was a very big mistake that carried on until today, basically. However, since 1920, this is the historical evolution of measurement of the Hubble constant. It started up here with a very big value and then came down, but since about the 1960s, it remains more or less constant. And look how many measurements there are there. So the first Hubble trouble here. The universe is younger than the Earth. But that was a question of the size of the error bar. Of course, these error bars were underestimated because they were systematics back then. And so the next thing is the Friedmann equation. This here is the 100 year from the Friedmann equation. Remember, the Friedmann equation are based on GR plus the cosmological principle, FRW metric, and there's H there. And then I can rewrite them in a little bit more modern terms where the cosmological parameters have appeared. And now the interpretation is basically saying what Wheeler said of GR, space-time tells matter how to move, and matter tells space-time how to curve, but how to move, that's the expansion rate of the universe. So basically, since you write the equation like that, I can say that the cosmo race is the space race, cosmo race. The development of cosmology could be summarized as the effort to constrain the parameters on those equations that are the cosmological parameters. This was an effort, sometimes competitive, sometimes collaborative, mostly a coordinated effort. And this brought us the standard model of cosmology, which is the extremely successful lambda CDM model, where few cosmological parameters, just 6 numbers, describe most of the observation, maybe all the observation we have of the universe across 14 billion years of evolution. There are parameters about the composition and the background evolution, and there are parameters about the perturbations and how the initial perturbations grow under gravity. And the model parameters are now determined with 1% or even better accuracy, and this is what we call precision cosmology. And the triumph of precision cosmology could be summarized in this plot from Planck 2018. I'm sure you all heard about the Planck is a NASA mission to observe the cosmic microwave background, the light of the early universe, and bang. These are the constraints on the key cosmological parameters. And if I were putting this in the same plot as, say, 20 years ago, you wouldn't see them. So this has prompted people that study history of science to actually say most have been discovered about a large-scale structure and history of the visible cosmos in the last 20 years than in the whole prior human history. Good. Never mind that the model is weird. The model has dark matter, has dark energy, has neutrinos, has possibility of other things there that are constrained to a level but could still be there. So the lambda CDM model, it's not really a fundamental model. It has connection with fundamental physics, of course, but it's not a fundamental model. We know that at some level it's an effective model, and when you push effective model, eventually something is got to give. You know that, right? That's the name of the game. The fact that it works so well actually makes it interesting, but likely it's an effective model. So let's go back to the Friedmann equation, and H is everywhere. And the physical densities, when you think about the early universe, also are those parameters with some H's with them. So if I tell you find h, you could just say, well, okay, do what it says in the can, distance versus redshift, and find h. So if you do that, then you need to build yourself a cosmic distance ladder. And what is of interest for us, there are 2 key ranks and 2 key steps. From the geometry, from say parallax, from the nearest star. I mean, there's a big Gaia group here, so I'm sure you know what I'm talking about here. From geometry to Cepheids, the same of Henrietta. And then from Cepheids to supernovae, because in order to measure some global background parameter of the expansion of the universe, you need to be far away enough that peculiar velocity due to the inhomogeneities are small and can be subtracted out, and they are not dominating all these recession velocities. So recall, type 1a supernovae, which are the ones that enter into this game, are standardizable candles and can be seen extremely far away. That's why they are a perfect object to do this game, to play this game. Type 1a supernova gave us the accelerating universe and dark energy of lambda in 1998 and the Nobel Prize in Physics in 2011. So there is very little wiggle room that we have with play with supernovae. And I'm saying that in supernovae, we were trying to measure an acceleration. When we try to measure the Hubble constant, we're trying to measure a velocity. So if you say maybe the Hubble Space Telescope, the calibration, the way you use the instrument is not stable enough, remember it was stable enough to get the acceleration, and that acceleration has been confirmed in any other possible way, so we have very little wiggle room to put all the blame on the supernovae later. So here is the cosmic distance ladder in a less of a cartoonish way and more professional way. So there geometry to Cepheids, and then you go further out, and then you have the Cepheids to supernovae, and the Cepheids give a 3% distance per source, and they are very luminous, up to 10 to the 5 solar luminosity, so they are visible up to about 50 megaparsec away, which make it nice to then calibrate with the supernovae. And there are other approaches to skip the Cepheid step, and we're going to touch upon them later on. And then since the end of the last year, there are some more than 40 objects where there are both Cepheid and supernovae, making this distance ladder very stiff and reducing any possible systematics, because you have in the same object both rank of the ladder. So, okay, find h, you do what is in the can, distance versus redshift, but also in the right-hand side of the Freeman equation, there is h. And so h is a parameter of the standard cosmological model. And we have a lot of observation that gave us the standard cosmological model and gave us its parameters. Let's look at, for example, the Planck image of the cosmic wave background in all its glory. This is the temperature bump. This light is also polarized. There's a wealth of information that has been extracted from this. And then observation of the later universe comes in the three-dimensional distribution of galaxies, large-scale structure, feature of assertion line of the light of distant quasars, weak gravitational lensing distortion of background light from foreground structures, all of that. So H is everywhere and is very special. But remember, we mostly measure redshift and angles, but we think in terms of distances. So that's where H comes in. We even invented units for H, the damn you little h, famous paper, where H naught is 100 little h kilometer per second per megaparsec. But H is a key cosmological parameters. So we have 2 cosmic speedometers. Read what it says in the can. Cosmic distance ladder based, recession velocity distance, and a global cosmological parameter of a model that is extremely successful and has been supported by many different kinds of data of the observation of the universe over 14 billion years of cosmic evolution. So this is a tale of 2H. A priori, these 2 numbers do not have to coincide unless the model is correct. If they coincide, then the adopted cosmological models survive an extremely stringent test, especially as the error bar on this parameter on both sides starts shrinking. So for almost 2 decades, these two H's agreed. And what happened in these 2 decades? Well, this happened. We started with COBE in 1992, beginning of the 90s, when we started talking about this standard cosmological model. And this model survived unscathed, this beautiful evolution of the data. This is even the impression of the polarized CMB light. And on the large scale structure side, even visually, at the beginning of the 90s, this was the state of the art, the stickman in the CFA strip. Each dot is a galaxy, and this is a slice through the universe. And then you go on to do BOSS, and then BOSS and eBOSS, and then DESI. And this survey here will fit in a little corner here, yet the model survived unscathed. So let's go back here. There was the first double trouble, and the first double trouble got resolved, understanding that the error bars were underestimated. And then we had the second double trouble there. You don't see anything about the measurement. The measurement keep being consistent. But this, look, this is the beginning of the 90s. What's happened there is that we realized that we wanted a flat, especially flat universe, but now we couldn't put all the content into matter. And then if we say, well, we don't put all the content into matter, we relax the flatness. We don't like it. So we keep the flatness, we put all the content into matter, and then we again have a universe that for this value of the Hubble constant is younger than the oldest stars. So there's another crisis in cosmology, and we know how that ended up. We have the cosmological constant. The cosmological constant sorted it, so that was the second double trouble. But the Hubble constant remained constant. The measurement remained constant until well into the 2010. And then something happened. So let's zoom in. And this is what happened from the 2000, the error bars shrink. You have the Cepheid-based measure, cosmic microwave background-based measure. They all agree until 2013. And this is a new measurement called tip of the red giant branch, and I'm going to say a few words about that later. And the final measurement from the earlier this year is 73 plus or minus 1 kilometer per second per megaparsec. So what's going on here? Some part of the community says this is a crisis in cosmology. New Scientist, Scientific American, you name it, all have a crisis in cosmology. But let's go back to this tale of two ages. If they coincide, the cosmological model survive an extremely stringent test. But if they don't, errors in the data, errors in the analysis, or errors in the model. There's some unknown there. We can wave our hand and say it's unknown, or we can try to figure out what is this unknown. In reality, there are many H-naught. Now, this plot changes weekly. So I did this plot yesterday afternoon. Not all measurement measure directly the current expansion rate, right? So this is the Cepheid-based measurement, measure the current expansion rate. This and this are trying to do the same, but not relying on Cepheids, bypassing the Cepheids, uses maser and uses surface Brighter fluctuation. This is a very cool measurement. The unfortunate thing is that there's only very few masers out there, but basically one can do direct geometry on things that are a cosmological distance. It's very cool. This is the cosmic microwave background. This, I'm gonna say a little bit more what this is. But this is based on early time physics. Again, this is the global parameters of the model. And this is the Carnegie-Chicago Hubble project, which is similar to what these do, but based on some tip of the red giant branch, a different feature in the color magnitude diagram of groups of stars. So what's the general thing that we read here? Models that do distance versus recession velocity, or models that are calibrated at redshift 0 tends to cluster here as methods, and methods that used early universe physics that are global parameters of a model tend to cluster there. And if you take this measurement and this measurement, it's more than 5 sigma, but there's more than one measurement there. So these are model-dependent measurements. These are cosmological model-independent measurements. So these are the two camps, the 68 camps and the 73 camps. And that's where it comes from. So I want to say something about this tip of the red giant branch measurement. So what's going on? You have a main sequence star. The main sequence star burns all the hydrogen into helium, and burns the hydrogen into helium. Then it burns helium into a shell and increases the helium core that keep falling in. And then, you know, those of you that have studied stellar evolution, I'm sure they know about that. And then at some point, the temperature is reached for a very specific core mass, and a thermal runaway happen. And when this happens, all the stars end up having the same luminosity. And when this happens, then the star becomes very dim, and you don't see it anymore, which creates the helium flash a cutoff in luminosity. And so this can be used to do a luminosity distance relation, because if these objects are close enough, then you can calibrate the luminosity distance relation, then you can go farther away, not as far as Cepheids. These are dimmer, but you can use that instead of Cepheids. And this measurement gives you something around 70, something in between. And I would say that the stakes are high. If you put these two people in the same room, it's not recommendable. One of them does the tip of the red giant branch, the other one does Cepheids calibrate measurement. So in order to move on, let's just recognize that the tension is fierce, the jury is still out. Choose several calibrators, surface brightness fluctuation, masers, but Cepheids is still the best one. There are now TRGB and Cepheid distances measurement to the same object, and they agree, thanks to the Gaia data that did that. The differences in TRGB mostly come from this object here and from the Hubble flow from the supernovae, how you correct from the peculiar motion, and from the cross-calibration of supernovae. So it's a question of how to treat the supernovae. It's not a question of how to treat the calibrators. JWST, this was not a targeted observation, it was just a serendipitous observation, managed to confirm the HST results in terms of crowding for the Cepheids, but there are JWST observation, so more soon. For now, let's trade the TRGB as another calibrator, correcting for this, average out, and move on. So then I want to say a few words about baryon acoustic oscillation, because you saw them in the previous plot. So when we look at the cosmic microwave background that was so successful in giving us the standard cosmological model, we know that there are the photons that are coupled to the baryon, there are these oscillations that give us the acoustic peaks, and we observe the photons. But if there are these oscillations that give us the acoustic peaks, those oscillation remains on the baryon. So when the photons decouple and then stream through us and we observe the cosmic microwave background, the baryons are still somewhat displaced from the dark matter that doesn't participate to this oscillation, but they are coupled to the dark matter by gravity once the photon pressure disappears. And when we look at the larger scale structure, we see the dark matter in the sense that galaxies form on this scaffolding given by the dark matter. But the dark matter had a few billion years of evolution to fall into this potential well created by the baryons, as well as the baryon to fall into the potential well created by the dark matter. It's a little bit like, Newton and the Earth and the Moon. They all, fall into one another. But baryons are about 1/6 of the dark matter, so these baryonic oscillations that were so big in the cosmic microwave background should be small, but should be there, and gravity is the coupling. And since we know exactly the physics that goes on in here, this gives us a standard ruler. Well, rather than a standard ruler, it's a 3D quantity, so it's a standard bubble, but okay, you know what I mean. And this is the classic Alko-Paczynski test. So you can do an Alko-Paczynski test, but also you know the length of the ruler. And the advantage is that this standard ruler, while here can be seen at one given screen and only in 2 dimensions, here can be seen in 3 dimensions and at several different ratios. So you can map the expansion history of the universe, you can map the geometry. So the ruler is the sound horizon at recombination for the CMB, a radiation drag for the larger scale structure, but the two are so close to each other that it's basically the conversion. It's basically the same ruler, and the symbols are RS or RD depending on who you talk to. So for showing how beautiful this is and how precision cosmology has evolved, these are the two key plots of the detection in 2005 of this feature in the large scale structure by SDSS and by the 2-degree field galaxy redshift survey. In the SDSS, in the Sloan Digital Sky survey was in the correlation function. In the 2DF, it was in the Fourier equivalent, which is the power spectrum. This is painstakingly low signal to noise, but was good enough to actually see it. And now this is from the EBOS in 2020. And there are people in my group that were involved into this analysis. And now you can do the same thing at several different redshifts along the line of sight and really map the geometry of the universe. So let's recap. Physics, the sound wave in the early universe propagate until radiation and matter decouple. This imprints a scale that is a standard ruler, which is a key observable and is useful to study the expansion history of the universe. We assume that you know the early physics, the early universe physics very well, and that's what sets it. Cosmic microwave background and early universe physics in the Lambda CDM model constrain the length of the standard ruler to 0.2%. And then for the aficionados, you can do two types of measurement. One thing you can do, you can say, well, I know the length of the standard ruler, so the symmetrized size, both along the line of sight and on the plane of the sky, if you are here and look out, will be smaller farther away and bigger nearby, so I can measure distances that way. Excellent. But you can also do something else. Remember, you measure distance, you measure angle and redshift, you don't measure distances, and now you're thinking in terms of distances. So if you use the wrong geometry and the wrong cosmology to convert your angle and redshift into distances, something that should be spherically symmetric because you have a standard bubble become squashed or elongated along the line of sight because of that. And so that's the classic Alko-Paczynski test. So both of these quantity can be measured. So let me repeat, it should be evident that since one measures only angle and redshift, if the standard length is not known, one can measure the relative expansion history, so E of z, omega matter, but not H naught. But by marginalizing over the expansion history now, you can get the standard ruler in combination with H, but you can never get the standard ruler alone or H alone. But you can measure these two. Why am I saying that? Well, and why is this becoming important relatively recently? So we do have standard candle and standard ruler. Standard candle is what gave us lambda. They are the supernovae. They give us relative distances because there is a large uncertainty on the absolute magnitude of the fiducial supernova, but they are standardizable, and that's what gave us lambda. Baryon acoustic oscillation can measure absolute distances, depends on the value of the sound horizon radiation drag, and is set by the early time universe. So now you can do a cosmic distance ladder that goes from here all the way to 14 billion years ago. How does it work? Well, the traditional, and we were able to do that only started 2015, not earlier. The traditional direct cosmic distance ladder, you measure a node, calibrate the supernovae, and then the moment the baryon acoustic oscillation became powerful enough that they could be meaningfully calibrated over the supernovae, then one could extrapolate the distances all the way to the early universe. But then one can also do another thing. One can take the the inverse cosmic distance ladder. You take this standard ruler, bring it down to the BAO, calibrate over the supernova, and go back at redshift 0 and give us H naught. And later on, where it's interesting, it's in 21, you can do a reconstruction, an S-spline reconstruction of the expansion history, so you don't even have to assume a physically motivated model. You just say, some parametric reconstruction, and you can still play this game. So in other words, what this is telling us that an H naught problem can be transformed into an RS problem and vice versa. So this thing became obvious in around 2016, where You have the age, you have the calibrator at redshift 0, the calibrator in the early universe, and different type of observation give you different constraints on this plane. Early universe does this, Cepheid-based measurement did that, baryon acoustic oscillation uncalibrated give you this, and you already see what's going on. 3 lines on a plane, not necessarily cross all in the same point. So basically, H0 is like threading a needle from the other side of the universe, or an end-to-end test. And the name of the game since 2016 or so was to make this ladder as stiff as possible. And what remained there is that the ladder is stiff enough, there's some wiggle room, but not enough to explain this 9% mismatch between the two ends. So 2 ladders always need 2 good anchor points, and these 2 anchor points seems to have a mismatch. So question, is there a problem? And the answer, I think, almost a decade later from when this issue first came out, is yes. However, how much of a problem is cosmological model dependent, and will also dependent on which type of data you want to put into the analysis. The latest Shu result tells you that is 5 sigma. And at the moment when it is 5 sigma, then you can't really swipe it under the carpet, and you may want to take a closer look at it. So now the next question is, where is the problem? And you know, all experiments are skeleton in the closet, and they may have systematics, but this is becoming increasingly unlikely. The things has been there for almost a decade. Many people have reanalyzed the data. Almost all the data, except some of the TRGB data, are publicly available. Anybody can go and reanalyze them. So you can imagine it takes time, it takes discussion, but nobody has found anything beyond the level of alpha sigma. So one working hypothesis is an early versus late. We realized that there's not much wiggle room in the middle, and so it's a question of anchor points. And so let's keep asking, what is the problem? What is the problem? Is it in any specific data set, keeping the standard lambda CDM context? So for a while, some people put the blame on the Planck data. If you remember in the first plot, there was agreement until we had WMAP, which had lower resolution than Planck. And then Planck came along and whoop, we had a problem with age. But I think since 2019, thanks to the work of Neil Schonenberg, who is also here now, they show that you can throw away CMB data completely. You will have to assume a prior on the baryon density that comes from BBN, Big Bang nucleosynthesis, and then the observation of late time abundance of the pristine element. But then you can drop CMB and you still have that early universe calibrated H0 measurement agree with the cosmic microwave background-based measurement. This is the technique called BAO plus BBN. So that is the 2019 paper. This here, he redid the analysis with updated data set, updated BBN constraints, wider selection of library of models. The result doesn't change. Basically, it gets more precise, but the central value doesn't change. The problem is still there, even without CMB. So the early universe is stubbornly in the 68 kilometers per second per megaparsec camp. And no, it's not in any specific data set. So a big effort by Di Valentino and collaborator went through the different possible data set combination and to see if the result, this dichotomy, was driven by any specific choice of the data set. They did all the possible n factorial combination, and the answer is no. So what is the problem? It's not in the CMB data. All early universe-based determination were well below 70 kilometers per second megaparsecs. Many groups reanalyzed the Shu's data. Several independent, low redshift calibrated determination who were above 70 kilometers per second megaparsecs. TRGB, I think the jury is still out. We have to be careful about the peculiar velocity correction, but work is going on there. So as the time goes on, this seems less and less likely. So where is the problem? If not in the data, then maybe in the model. So the last time somebody tried to do that, my countryman, it didn't end up too well. So we got to be careful about what to do. So I give you my personal partial view, and I'm happy to discuss. So let's see, we can do pre-recombination solution or post-recombination solution. Pre-recombination solution modify the model right where we most like it, because a lot of the success and the precision of the Lambda CDM model came from the cosmic microwave background and the early universe. And this means that we have to modify the sound horizon radiation drag, that is the sound horizon R recombination for the CMB, which is this simple-looking innocent equation. We need to decrease it by 7 to 9%, but without breaking havoc on the CMB damping tail and everything else. And this is a tall order. It's hard to do that. So one of the very promising proposal was to invoke some sort of early dark energy, just to say, look, you have some period where you change the expansion rate of the universe due to early dark energy, and then this one disappears. We have some late time dark energy. We had some inflation that looks like some dark energy. Why not having another one in the middle that fixes this problem? It turns out, by Knox and Millea and Euler et al., that if you want to do that without breaking everything else at the high redshift, you have to touch the model, not everywhere. So you can't just say, I have some dark radiation, some extra neutrinos, and I leave it there. That doesn't work. The damping tail of the CMB goes out of whack. You have to do it slightly before equality. It needs to come in very quickly, and then it needs to die off very quickly. A recombination or just before recombination, otherwise the damping tail of the CMB tells you can't do that. And also you have to be careful about messing around with the matter radiation equality, because that's also constrained by the CMB. So that's the solution called early dark energy solution, and that's the room for maneuver to reduce the sound horizon radiation drag. Reminds me a lot of fine tuning, but sometimes it's good to have fine tuning or designer model. It tells you where to go. So there are other options. Change of initial condition, extra component, extra energy injection, high temperature recombination, designer model, etc., etc. These are not all equivalent. So new data will tell us which ones are ruled and which ones are ruled out. So what about post-recombination? Well, you could think about screening, modification of GR. I think it's complicated because you will have to have several things at once. You can increase the freedom of HFZ, again, a designer model, but the price is high because you are adding many degrees of freedom, which reminds me of AP cycle, and then or hide it where there are no data, and then this reminds me the Russell teapot kind of argument. It's very hard to change the sound horizon by at least 7% without breaking everything else. And it's also hard to mess around with the standard rule RRC in the BIO. You can say, okay, whatever, the CMB is right. But then by the time you want to impose that signature into the larger scale structure, peculiar velocity, baryon velocity, they are displaced with respect to the dark matter. And then that feature is displaced. And that's why you infer the wrong age. And it's very, very difficult to get it to the 9%. You break everything else. So one approach that came out last summer was, again, by Niels and collaborators, to just do the Olympics, to just take all the models and just give them a fair ranking, and then give them medals depending on how well they perform to fix the Hubble tension. And some of them get bronze, some of them get silver, and some of them get gold. The only viable one turns out to be early time solution. Late time solution are disfavored by the data. That is, they're disfavored by the data. Okay, so then my question is, if we're saying that we don't trust the model, then we are testing the model. So how can you do that with the model? Can you do without the model? If you are testing the model, you have to drop some of the assumption of the model, otherwise it may be that you are in a circular argument. So, as Feynman said, the first principle, you must fool yourself, and you are the easiest person to fool. So maybe one approach is to try to be a little bit less model dependent. So one approach we try, I mentioned it already, is to try to reconstruct the expansion history that is not the absolute expansion history, but the relative. So h of Resch is a function of h naught with splines. This is not a physically motivated model, but it just tells you, assume that you give it as much freedom to the data as they want, what did they come back with? And the result is basically there's no much freedom there. You have more freedom because you've added extra parameters, but it's not enough to give you that 7 to 9% mismatch. So here we are. We're looking for Cinderella. We have to find a model that fits shoes. So what could be the hints for model building? And I think that even in a model independent way, this statement is still true. Right. Post-recombination solution do not appear to be too viable. And I would say that this is a problem that goes beyond H0. We call it H0 tension, but it goes beyond H0. It's also an omega matter problem, and it's an age problem too. So if I redo the plot I showed you before, now in an omega matter H square plane, again, I can write down 3 independent constraints, and they don't cross all at the same place. So you have also an omega matter problem. And you also have an age problem. So in other words, the way I'm going is that we are going towards being a tight spot because the observations are becoming constraining. Even variation on the lambda CDM model, even in variation, we have several over-constrained systems. You can measure independently omega matter, H0, omega matter H square. You can measure H0, the combination sound horizon radiation drag time H and the sound horizon radiation drag, age, H0, and age time H0. And then more about this later, you can measure equality scale, omega matter H square, and H. And you can think in terms of laterly time quantity, or you can think in terms of physics rather than model parameter. But with each of these combinations, we use different observations, rely on different physics, and test the different aspects of the model. So the idea is to see whether this gives you guardrails of where you can go with a new model and where you can't. Now, this is a more complicated game than just fitting parameters, but if you don't know what the right model is, maybe that's the way to go. So another question you can ask is, how old is the universe anyway? This is back to the 90s, where the age of the oldest star told us that there was something wrong with the universe. So this is age of the universe versus H0. That's the shoe measurement again. In a lambda CDM model, BAO plus supernovae give you something like this. Planck is down here, and the age of the oldest globular cluster should be able to tell you where you are in terms of the age of the universe in this direction. And this was the PhD thesis of David Valsen. He put a heck of a lot of work into it. And from the state-of-the-art data set of oldest globular clusters, he selected 22 out of almost 70. He gets an age of the universe that lands there. So it's in agreement with the early time age, but not in agreement with the late time calibrated age. Before I conclude, I want to tell you something about a paper that actually doesn't come out yet, but goes right to this problem. Large-scale structure was very useful. It gave us a baryonic acoustic oscillation, direct and inverse cosmic distance ladder, a cosmic distance ladder even without the CMB by using BBN. But I say your large-scale structure gives you more than one H. And this is how it goes. The baryon acoustic oscillation can give you an uncalibrated expansion history and some omega matter, or an early universe calibrated H0. The relative growth of structure through ratio space distortion can give an omega matter constraint, although this constraint is still weak. But the large-scale shape of the power spectrum on large-scale structure can also be used, and this has information about matter radiation equality. Now, I'm not saying anything new. This is back down memory lane. This is back in the early 90s, the famous BBKS paper, the one that's got more citation than anybody else because of a fitting formula in the appendix. That fitting formula gives you the shape of the matter transfer function. And the shape of a matter transfer function has an important parameter, which was called in that original paper big gamma. And big gamma basically says, when the universe is radiation dominated, perturbation inside the horizon can't grow, perturbation outside the horizon grow, then at some point the universe becomes matter dominated, and then the moment it becomes matter dominated, all the perturbations start growing. So an initial power, low power spectrum will change its shape, and the way it changes shapes depends on how the horizon, how fast the horizon is traveling before matter radiation equality, or how fast modes are entering the horizon around matter radiation equality. So there's some information about matter radiation equality. So this is a transfer function from the BBKS. There's also the wiggle due to baryonic acoustic oscillation. At the BBKS time, we didn't know that. But there is also a suppression to the baryon content part, which is, in this plot you can't see and was not in the original paper, but the paper like Eisenstein and Yu in the mid-90s put that in and based that on a very strong solid footing. So what happens if I now change matter radiation equality? If I change matter radiation equality, the transfer function remains 1 here, but it moves this way. And so a slope there, now this is my not really artistic way to do animation. As you move it, you're going to change the slope if you measure it around the same vertical point. So this gives you another speedometer. That is how fast the horizon was expanding just before equality, or how fast modes were entering the horizon just before equality. Now you have a speedometer, but at early time. So measure a late time from the imprint that this left on the structure, and on linear scale, so it should not have been affected by nonlinear evolution. So this gives us yet another H. So if the standard BAO analysis in the H omega matter constrain things like this, depending on which redshift one observes, this large scale feature put constraints in this direction. Or in other words, if you now want only early time quantity, you can marginalizing over the expansion history of the universe and get an RD times H constraint. That's here. And then the large scale constraint, this equality based, give you a constraint here. Now the bands are from the data, but I'm going to show you a better plot in a moment. So long story short, from the slope, you can read K equality in megaparsecs if the baryon content is approximately known by BBN, and if no other effect change the shape of the galaxy power spectrum of those scales. Non-Gaussianity, anyone? We're going to talk about it another time. And so, and this is what the state-of-the-art data say. This is the combination of BOS and eBOS data. And we could do that because we have Hector Gilmarin here who work on both surveys, so has the hands on the data, and a lot of the work was done during the PhDs of Samuel Bryden here. So the BAO constraints are here. The equality constraints come down here, and they cross. And they cross right where you would expect them to cross in a Planck-calibrated lambda CDM model. They don't cross at 74, which is what shoes want. And you can say, okay, maybe an early dark energy model can take all this line and move them because I've misinterpreted the sound horizon and radiation drag. But look, if you move this line in order to move it down here, you have to be careful, because then we may not cross with these other constraints or with the omega matter constraints from the same large scale structure data. So again, you have an over-constrained system relying on different physics. This is late time physics, this is equality, and this is just geometry, or if you calibrate it on the BBN, is the standard ruler. And there are two ways. So I show you the slope, but in principle, one could also use K equality as a standard ruler, the same way we did it for that. So let me go towards the conclusion. In early time pre-recombination solution, you can't just mess around with sound horizon. You have to present the agreement with matter radiation equality scale as seen in the large scale structure and hopefully also as seen in the cosmic microwave background. And on top of that, remember sigma 8 too. We have another brewing partial curiosity, not yet tension, with the amplitude of perturbation. So being a tight spot means that we now have several well-planted guardrails on the road to a model which can explain away the Hubble troubles. And the theoretical solution should not break Hubble where not needed, should preserve the good agreement of lambda CDM with data, should improve or at least not worsen other tension, like the sigma 8 one, and we should quantify improvement versus predictability, and in terms of degrees of freedom, this is a parallelism with what we were doing when we were introducing lambda, like in the mid-90s. We should make sure to divide between model-dependent and model-independent approaches and ask ourselves at what point we are at in epicycle. There are two different types of epicycle. Look, this is the Cassini, the Earth-centric model, and this is the Copernicus, the sun-center model. The sun-center model of Copernicus still had epicycle, but this epicycle were not leading anywhere, while this epicycle were leading to the fact that the orbits were not circle, they were ellipses. So there are some epicycles that actually lead you on the right track, and we have to be careful when we add the epicycle, we want to add these and not those. So, summary. The discrepancy between model-dependent and model-independent determination of H0. And I would argue that even in a, so if the problem is not in the data, then maybe it's in the model. You could boost the expansion rate before a combination, fixes the ladder, but beware we have more than one ladder, and the low redshift solution have very limited wiggle room, and the trouble goes beyond the H0 and the distance ladder. And I would argue that you can try to do that in a model-independent way. So when we look for Cinderella, I would say that if the ITU is confirmed, right now there is only one measurement by my PhD student. It will be good to see independent measurement done. Model with IH0 and standard low redshift physics has this favor. If the shape measurement, since the paper is not peer reviewed yet, is confirmed, then reduce wiggle room to change early time physics. So I'm going to stick my head out and tell you that there are two possible scenarios, I believe. One local, affects a very local H0 measurement, astrophysical or cosmological, think screening, stellar properties, and leave everything else unchanged, including the line of sight integral are seen in the BAO and in the low redshift supernovae. Or a global one, but then the physics affect the entire history, probably both early and late, because it was impact quantity well beyond H0. But it will show up in new cosmological observation, and we are narrowing down on what to tinker with respect to lambda CDM and what not to tinker. And so I think this is a good place to actually remind what Sherlock Holmes said. And I'll stop here. Thank you.
Thank you, Licia. Now it's time for questions.
Yeah, okay. So for the early universe probes, everything is based in the end on the sound horizon.
So the CMB and the BAO, yes, but the quality one, you marginalize the sound horizon away. So it's not based on the sound horizon. Okay. But there is one thing in common, which is if you want to use CMB, you need to use BBN.
Okay. Yeah.
So you would have to really screw back BBN.
Okay. Well, I was thinking, one way of changing the sound horizon, at least for the methods that use it, would be to recompute it in presence of magnetic fields and turbulence, for example. It's known that the speed of sound changes in a turbulent medium. So I'm not an expert in plasma physics, but so I don't know how this would change in the plasma we have in the early universe. But in tokamaks, for example, sound speed changes a lot with magnetic fields and turbulence. And it could even change with time. I mean, cosmological time. And without breaking anything else, because then
well, you would have to assume that you have a strong primordial magnetic field that actually do that, and it's very difficult to see how to do that. So what I'm saying is that since now we have a different ruler, which is based on equality, if we are just at the limit that maybe we could move the sound horizon and the equality, don't move it, maybe we are at the limit. If we reduce the error bar just a little bit, then whatever you come up with needs to fix the H naught at redshift 0, needs to move equality and sound horizon coherently. And I don't think magnetic field can do that, because in the equality, they don't change the way the modes enter and re-enter the horizon. So, yeah, I think let's wait for what Desi has to say in a year's time.
Well, one could still do plasma simulations with turbulence and magnetic fields. I don't think it has been done.
Yeah, but I think because it will be hard to explain people how you can put a strong enough magnetic field that then don't mess up the polarization of the cosmic microwave background, because there is a very good agreement between the temperature and polarization. Right now, half the signal from cosmology come from temperature and half come from polarization, and they agree. So there is limited wiggle room, although I don't know if anybody has quantified how much mismatch you can still put in such a way that.
Yeah, so I wanted to ask about this new, the quality scale. So it seems to me, this of course must depend on n effective, and people have used this before. So people have used this before in a way of saying, assuming the model we use, right? Let's use this as a measure of n effective. I guess both from the CMB and large scale structure, and it's consistent with the standard model. So I suppose now what you're doing is, let's assume n effective is 3.046, right? There's no other surprises, and then let's use this as another way of measuring H naught. Okay. But so wasn't that?
Yeah. Okay. So there are several ingredients in order to be able to read equality out of the slope of the large scale power spectrum. One is that the bias behave on those scales, if we believe it behaves, these are linear scales. One thing is that there is no primordial non-Gaussianity, because otherwise the bias will be scale dependent, and that wouldn't work. The other thing is baryonic suppression, then you need BBN to know baryonic suppression, and that's where the N effect. And the other thing is you need to know NS, because if the primordial power spectrum has whatever shape you want, then of course you can get a slope that depends on the feature in the primordial power spectrum and not on the feature that you are measuring. So we are assuming a power law primordial power spectrum with an NS that is broadly supported by inflationary models. So it doesn't deviate too much between 0.96 and below 1. On N effective, until before 2019, in 2018 or so, it's true, you had, with BBN, you had a complete degeneracy between omega baryon and N effective. And so you could plot omega baryon and effective, and you would see this degeneracy, right? And then if you only cut at an effective 3.04, then you would get some nice constraints. So that was based only on the deuterium abundance. The moment you add the helium, then you break the degeneracy. And that came out in 2019. And then we use those constraints. And so you break this degeneracy, and if you add an effective, you release a little bit, relax a little bit, but not too much. But you really need to rely on BBN. So you could mess up BBN. I don't know if we want to do that, though.
You said that post-recombination solutions don't look good. what about a time-varying lambda? Is that viable, or is there something that obviously goes wrong with that?
So a time-varying lambda will be basically equivalent to a quintessence kind of model, where you assume that omega lambda doesn't, it's not constant, but it scales with some equation of state parameter, etc. So it turns out that if you only look at the two anchor, you say, well, a W less than -1, which is already a very weird quantity, would do it if you only look at the two anchor. But if you now look at how well we know the expansion history coming from supernova, because we have a lot of supernova, both low redshift and high redshift. Baryonic oscillation also, although baryonic oscillation start getting a lot of their statistical power at redshift above 0.5 because there's enough volume. But if you put these two together, it turns out that that W, at least as a constant W less than -1, it doesn't work. You could think something like, well, maybe we are in the center of a void, and therefore we do have some sort of acceleration, which is like saying it's a W, but the change very, very locally. So if you want to do that in terms of actual velocity, that will create a kinetic Z effect, which we would have seen in the cosmic microenvironment, which we haven't seen. So again, so there are guardrails everywhere. And they are hard to evade.
Any other question? Okay, so I think since Licia is here, we can continue asking her when she's around. And I just, so let's thank Licia again. And I just want to remind the students that Licia will be available for talking to them today at 3:30, I believe, in the Blue Room.
Thank you.